Any thoughts yet? That's okay. It'll come to us. It'll come to us. Okay. Well, let's see what we actually do get when we minimize our function. Oh, question?
No. So the question was, what sort of transformations in C would keep the energy constant, right?
Yes.
Unitary transformations.
Unitary transformation. Excellent. So should I pre or post multiply my C by a unitary matrix?
Post.
Post. Very good. D is unitary. Right? Namely, D dagger D equals D dagger is the identity. If you want to check that, just notice that what's going to happen to P under that transformation, and everything does depend upon P, is C would go to C hat times D, right? Times C hat dagger, which is C hat dot D dagger. Remember, the C's are expansion coefficients. And then, of course, that just gives me, hang on a second here. Right, C times D dagger times C dagger. D dagger is the identity because it's unitary. And I have left then the density matrix invariant, and therefore, since the kinetic energy only depends upon it, and the density also is dependent only on it, the entire energy is invariant under this. Now, post-multiplication does what to our wave functions? So let's remember that our wave functions basically are the columns of the matrix C, right? Those are the expansion coefficients for our wave functions. This is what C looks like. D is some square unitary matrix. And by rules of matrix multiplication, if in my example I've got 4 things going across the top, then it's got to be a 4 by 4 matrix. Unitary matrix, of course. That's D. And when I take this product, what is the effect of post-multiplication on these columns?
Linear combination.
It takes linear combination, right? So if I take any unitary linear combination among my wave functions, the energy won't change. So, for instance, if my wave functions actually were the eigenstates, I could mix them up and scramble them up by taking some unitary linear combination of them, and the energy would be exactly the same. So, when I minimize, I don't know what unitary transformation I'm going to end up with, because they're all just as good. And that's the essential problem. Getting the eigenstates. Nod your heads, does that make sense? So, let's see what we can do about it. Well, I think it helps to, again, look at what we'll find at the solution and see how that relates to the eigenvalue equation. So at the solution, we have, of course, 0 will be the gradient with respect to my wave functions of the energy. And I had written that expression down now a couple of times, but I'll do it one more time. We had H times W times U inverse minus O times W, U inverse, W dagger applied on HW. And both of these guys, actually, let me put a bracket here. Both of these guys had a U inverse on that back end. I like to draw it this way, yes, all right, well, certainly the U inverse is no problem, right? Because this guy's going to give you 0, then I can simply set these two equal to one another. So I'm going to find then at the solution point, actually, do I want to make that point right now? I'm just thinking, hang on, guys. I just want to see which space I want to do this in. Right. Let me just make one extra step. It makes the algebra easier. You come to the same conclusion. So let's suppose I've minimized. Right? Suppose we find the minimum. Right now, of course, the W's are not necessarily orthonormal. Right? So why don't we orthonormalize them? Let's give us a little closer to maybe what the eigenstates are. So as we find a minimum, let's replace W with the orthonormal version. So I'll let W prime be W times the orthonormalizing matrix, like that. And then let's look at the gradient at that point. Right? It should be just as good a solution. I've just gone to my orthonormal wave functions immediately. And at that point, then, because they are orthonormal, I will be able to read off h times W equals O times W times U inverse, but now at least U inverse is the identity because I've become orthonormal, times W transpose H W, which is some other matrix. And that will be the equation I satisfy when I get to my minimum energy, once I've orthonormalized. Right? Okay, now. Let's take a look at the equation we would really like to solve for the eigenstates. Now for the eigenstates, I have to kind of go back to the beginning to the eigenvalue equation. We expect we're going to have something like this, right? Minus 1/2 del squared psi I of x, or r, I guess I've been calling it, right? Plus some potential applied to my wave functions. Gives me back the eigenvalues times my wave functions again. Right? And our wave functions, of course, have some expansion, and we're calling the expansion coefficients W here, W alpha I, times my basis functions, B alpha of R. And now I would like to turn this into some matrix equation, and the standard approach for doing that is what? Clearly, I'm going to insert my expansion in here into my wave functions, which will then give me a condition independently on every point in space, which are too many conditions. So what do I do to get down to the right number of conditions?
We multiply with V star.
Very good. So we're going to insert this in there, and then pre-mult and integrate with B beta star R. Both sides of the equation. So, let's see. When I integrate B beta star onto this term here and insert this expansion, I can just go rearranging all my terms. And the first term is going to give me something like minus 1/2. There's my sum on alpha, integral B beta star R del squared B alpha R d cubed R. So let's see, I've gotten my integral, my B beta, my d cubed R. I've gotten my minus 1/2, I got my del squared, psi I had this stuff, had the sum on alpha, got the B alpha but not the W, so there's a W alpha on that side of the equation. Plus something involving V, which we'll leave aside for the moment, that's not really where the focus is, equals then epsilon I, and when I integrate B beta star against psi I, I'm going to get, well, here we go again, right? Sum on alpha, there's an integral B beta star of R, and then of course psi I had B alpha of R in the expansion, and also the coefficient W alpha I. There's a QQR, and I can't quite fit it in there. Like that. So my equation is going to read, well, I'm going to define the same operators I always define, right? There's an L and an O. So what the first thing looks like is minus 1/2 sum on alpha L beta alpha W alpha I plus some linear operator on the W's that involves the V's. And then on the right-hand side, it's going to equal sum on alpha O beta alpha W alpha I times epsilon I, which I don't want to forget. Going into my matrix language, this will be minus 1/2 of L multiplying my matrix W, plus again some linear operator involving V, right, acting on W, equals the sum on alpha here, of course, gives me the product OW evaluated at beta I, and then times epsilon I. And how would I put this into matrix language? What is this in matrix language? I have this matrix, beta I, post-multiplied point by the scalar epsilon. Thoughts? Yes?
It's a matrix vector product?
Kind of, right? It's definitely, it's a kind of matrix vector product, but it's not, how do I put it? This is not summed on I. That's the tricky part. But let's get a sum going, right? So I can make this a sum on I. If I wrote this as delta ij, epsilon j, right? Well, I guess I've turned it into a sum on I, right? That would be a sum. What am I doing?
J?
That's going to be a sum on j. And then I could, wait. Then I could recognize this thing as, this is just a diagonal matrix ij, right? With these elements along its diagonal. This is diag of some vector epsilon, ij component of it, or ji component, whatever, right? It's a diagonal matrix. And then, or maybe I like the, it's like one of those things, you know how it's going to work, you can't quite get it right. Because this is a Kronecker delta ij, right, I should have made this a j, like so, right? Then when I do that sum on j will pick up the value I, then I'll get my appropriate answer. Finally then. So then, this looks like just the matrix product, OW times the diagonal matrix. Like so. Now I think we can try to compare. This is the eigenvalue equation. This is our variational condition. And what we can see is it has exactly the same structure, right? H on W gives me back some normalization factor times my W's, and then times a matrix. This has the same exact structure, right? Minus 1/2 L is H, part of H, and here's your other part of H. Gives me back O times W times a matrix. But to be the eigenvalue equation, this matrix has to be diagonal. And the problem is that this one may or may not be, depending upon which equivalent minimum, which set of states that gives me the equivalent minimum energy I happen to stumble upon when I minimize my function. So the last step of this then is I just need to find the right D, the right unitary transformation to use so that this guy becomes diagonal. Then I will have the states, right, that will satisfy the eigenvalue equation, and I'll also have the eigenvalues. So we want D such that we'll get a diagonal matrix. And of course, whatever diagonal matrix we get, those are going to be the eigenvalues we can read off of it. When W post multiplied by D daggered into H times W post multiplied by D, when I find the right D for that, and now I just do the algebra, right? D dagger, W dagger, HW times D. And by the way, this guy here is just the expectation of my Hamiltonian between all my different states. So we like to call this the subspace Hamiltonian. It's just the subspace projected Hamiltonian, subspace, or just HSS, which is some matrix of size, the number of bands by the number of bands that you have. So I just need to find the unitary D that will diagonalize that matrix. And then the diagonal matrix which it yields, of course, are my eigenvalues. And naturally enough, in MATLAB, there's some nice handy routines that will give you, for any Hermitian matrix, the diagonalizing unitary transformation and the eigenvalues. So that's how you get those. So that explains that comment on problem set 2. Questions there? All right. So, good. So we're all set for problem set 2. We're all set for problem set 3. There's just problem set 4 and these remaining optimizations that we can make. And I promise that there are about 6 orders of magnitude of memory savings we're going to be able to get. So, let's see if we can get those. So this is just the topic of additional optimizations. Now there are 2 that we're going to make. One is a purely numerical issue. And it's related to the fact that we have actually more basis functions than needed for the resolution on our grid. I mentioned this to you guys earlier, right, that oftentimes if you pick a good basis set, you won't need nearly as many basis functions as you would want to have real space sample points. And that's very true in this case. And that's going to save us. It's not going to save us 500,000. That will save us a factor of 16. That's nothing to sneeze at, right? So we'll take that, and we're going to look at that. And that's just a purely numerical feature of spectral methods you guys should be aware of. But that's purely numerical. The second one is more physical chemical. Oh, I undersold it, actually. Oh, there's another factor of 8. We're going to get 4 million. Okay. So, and this is going to then give us, well, I guess we go from 250,000. Right, so it's going to give us a factor of 250,000, which multiplied by this 16 times is going to give me 4 million. If I've done the math right. If I haven't, It's still pretty close. You get the point, right? I'm clearly teasing you guys. But I want to make a point here. That's why I'm teasing you like this. And the point is this. It comes back to, good practice of computation. In computational work, in solving physics problems, inevitably, right, the greatest improvements, the huge improvements, always come from knowing your physics, in this case, physics and chemistry. They always come from that. Numerical optimizations and tweaks and stuff are important, and they will generally gain you maybe an order of magnitude or two, right, kind of in this kind of a range. But the real improvements always come from physical insight. That's not to underplay, though, the importance of good numerical work. Because this factor of 16, in practice, will be the difference between you being the first one to carry out a certain calculation or understand a certain system and the next guy. Because, while he's run his calculation you go to the APS meeting, you get your idea for the calculation, right? Maybe it's a month-long calculation. That's typical for us, right? So the smart guy gets it done in 1 month and has his paper submitted. You are waiting around for 16 months and you're going to test. So these are important factors. And we're going to start with those here. But these are the ones that really make the big groundbreaking differences. Okay. And what this relates to, and we'll come back to it, is something known as pseudopotential theory. But since we're all grown-ups and I'm a very honest person, we should put quotation marks around the word theory. Yeah, people working my group know why that's funny, but you guys will get some sense. Okay, so the purely numerical problems. Where's this factor of 16? Well, the first interesting thing to think about, I think, is that in fact, we have a non-isotropic representation of space. So we are actually resolving certain directions in space much better than others. And you guys kind of know how it is. It's the weakest link in the chain. Our ultimate accuracy is determined by the direction which has the least resolution. And all that other resolution in those other directions is not doing us any good because we've screwed it up in the poor directions. And we're just wasting our time with that extra resolution. Now let's see if we can figure out where that is. So I'll draw it in 2 dimensions, but you'll see it carries off nicely into higher dimensions. So let's say we had some 2-dimensional square unit cell, and I have some grid on it. Maybe for the purposes of the diagram, make it 4x4 grid. So this is in real space. And actually, ultimately, it's going to be a little bit easier to understand in Fourier space. In Fourier space, we have the same grid, right? We have the same FFT box. In this case, it's going to be 4x4. This is in Fourier space. And real space. Okay, so can anyone tell me which directions have the higher resolution and which ones have the lower resolution on our little square sample grid here? Oh, I'll give you some hints and then I'll ask again, right? Well, let's see here. Well, it has cubic symmetry, right? So clearly, for instance, the resolution in the eastern direction is the same as the resolution in the northern and in the western and the southern, right? Those are 4 directions. They all have the same resolution. Then there's these other directions, right? There's like northeast is clearly different than east. There's northeast and whatever it is. Northwest, southwest, southeast. So where is it higher resolution? North, say, or northeast? Take this tab.
North.
North. Higher resolution. Good. And why do you say that?
Because
it's tricky, isn't it? Yeah, it is tricky. You're right to be a little... Right. I was tricked by that the first thing, too. No, the north actually has the worst resolution. How do I know? Well, remember, what determines your resolution basically is the corresponding Nyquist frequency. How short a wave can have plus and minus points going along your grid. Right? So in this direction, for instance, I could have all these points be plus part of my wave, all these points here be the minus part of my wave, and all these guys here be the plus point of my wave again, right? So that will give me a certain resolution. And my wavelength, going with my Nyquist frequency, is going to be 2 boxes, right? So if we want to calculate this, the associated wave vector, that would be 2 pi over that particular wavelength, and that particular wavelength is, well, let's see here. It's the, how do I put it? It's the size of my box, R, times 1 over n, tells me my, spacing between my blocks, right? Times 2, because my wave, I had 2 of those 1 over n blocks. Now, when I go off in this direction, the wavefronts will look like this. The first wavefront will be here, and I could make all of these positive points. And then you might think at first, and this is how you get screwed up in the head, right? You might think, well, the next one is going to be here. No, right. I could take this wavefront and make all of those points minus. So this will be plus, that'll be minus. This one here will be plus. Right? And that would nicely represent that kind of physical behavior on this grid. But you'll notice the wavelength is shorter here by root t2. So the reciprocal, the corresponding wave vector g then would be bigger by root 2. And maybe I'll run a little math here. So what did this give me here? 2 pi on r times n over 2. And here this then would be 2 pi on r times n over 2. Well, I have 1 over root 2 times the wavelength, so the corresponding wave vector will be bigger by root 2. This is a little easier to understand in the Fourier space. In the Fourier space, here's my reciprocal lattice vectors. Here, say, is my origin. And you'll notice I've got the 0 wave vector, and along this direction, the biggest wave vector I have is this one, which is closer in than the biggest wave vector I have off in this direction. And we can just triple check that this is what's going on. Well, this wave vector, notice, is my basic reciprocal lattice spacing, 2 pi on r, times how many points can I go out? Well, remember, I only go out n over 2 points before I have to wrap around and start doing the negative wave vectors. So it's 2 pi on r, n over 2, which is precisely what I did in this picture. So if you don't like the intuitive picture, well, you could probably buy that. And then similarly, this point up here we know is going to be bigger by root 2. So this resolution in this direction is higher. This gives me g equals, well, the same thing, right? 2 pi on r times n over 2 bigger by root 2, which is precisely what we had got from that little physical picture there. So we are wasting, all the space outside here because we are over-resolved. What we should do is we should take our worst resolved direction, namely this one, and then only accept wave vectors of that magnitude or less in our final basis set. So I should only accept these points in my basis set because these are just wasted. That's the point. Now, the quantity represented on the grid primarily is the density. Right? So for the density, what I want to do is I want to expand only in the inscribed sphere. And now we can figure out what the savings from that would be. Right? So the savings, of course, are the volume of the box divided by the volume of the sphere. And the box had size, well, these dimensions, right? It's, what's the size of the volume of the box? it's n FFT points, right, cubed. And the sphere has volume 4 pi on 3 times the cube of its radius. And the radius we're taking is n over 2. So then, well, the pi and the 3 will flip over. I'll get 3 on pi. And cubes are all taken care of. And I have 4 over 8, which is 1/2, flips around times 2. And 3 on pi is 1, right? Then 5%. So that's about factor of 2 savings there out of the 60. Just by not wasting your time with all these other basis functions. Now, if you guys are thinking about the total savings in the computer program, keep in mind we only have one charge density, but we have wave functions, right, for every single electron in the system. So very quickly, if we can compactify our representation of like the wave functions, then we'll really get some savings. This is just on the density. So the wave functions now, there's an issue with them also. So now, if we're going to have this resolution for the density, let's think about what resolution we need for the wave functions. So the wave functions, have these expansion coefficients W, and we're going to have them live in some sphere, right, like so. And then we're going to take our wave functions, psi, and we're going to construct the density, n of r, by basically summing up the squares of these wave functions. And they, ultimately, the density, I should say, is going to live in Fourier space in a sphere, as we've just discussed, which should be inscribed in my Fourier transform box. And the question I have for you guys is, how does the size of this wave function sphere, given the connection between that and the density, compare to the size of the charge density sphere? So these are the size, and those are the densities. Anyone tell me? We'll work it out. Let's see, the charge density is basically, right, psi of r, or psi star of r, times psi of r. And if psi of r is expanded in some plane wave basis set, alpha, what do I call it, w alpha e to the I g alpha dot r, right, star times some on beta, w beta, e to the I g beta dot r. Then let's see what I'll have. I'll have some double sum on alphas and betas, w alpha star, w beta, whatever, right? Then times a bunch of waves, e to the I, g beta minus g alpha dot r. So, if my wave functions exist in a sphere of a certain size, how big is the sphere for my charge density? So this tells me, right, that the Fourier components of my charge density are just the differences between all possible Fourier components of my wave function. So I can take any two wave vectors from within my wave function's isotropic expansion, and the difference between them then will correspond to some wave in the densities expansion. So this sphere is how related to that one? Go ahead. I think you said, I saw his lips move. No?
It's double.
Double, right, double. Right? Because, here's the origin, so if I have one wave vector here, the biggest furthest difference I'll get is when I subtract off that wave vector there. So the wave functions should live in a sphere that's half the size of the sphere that's inscribed in the Fourier box. That's the bottom line. So the wave functions expanded in sphere half the radius of the inscribed sphere. Or if you want like a simpler criterion, you would just say the magnitude of the wave vectors that you would accept have to be less than 1/2 of the wave vector in the worst resolved direction times G worst. Like that. Question. And then my savings, of course, will be let's see here. All right, savings, well, I have, well, clearly if it's got half the radius, it's half the volume, right? So I've got 8 from the doubling of the sphere from the wave functions to the density, and then a factor of 2 from the inscribing, and that's the 16 that I come for you there. Pretty good. Now we'll have to talk about how we implement this in a practical point of view. But that's the basic ideas. Basic idea. So I guess we can talk a little bit about implementing it. Okay. Now. What we're implementing really is an entirely new basis set. Right? It's a subset of the old basis, but it's a new basis set. And the nice thing about the framework we've built up is that it's very mechanical to swap out one basis set and swap in another. All the gradients and derivatives of the energy function, all that stuff just stays the same. And you'll be able to take your working code without the optimizations and just replace your operators and transforms. And so we just have to go through and figure out what the new operators and transforms are. New basis. And we need new operators, O and L, and new transforms. And those are what? I, J, J dagger. Did J dagger ever enter anywhere? I don't think we have it. Oh, well, it depends how it comes. It may or may not come up. But certainly I dagger appears in the expression for the Hamiltonian. Okay, so what is O? Well, we're back to our basic definitions. O is integral B beta star R, B alpha R, dq gar. We are still in a plane wave basis, right? We just have some different subset of wave vectors. G beta R star e to the minus I G alpha dot R dq bar. And we're calculating things per unit cell. Okay, well, it's still an orthogonal basis, right? So it's still the Kronecker delta alpha beta. And then when G alpha equals G beta, we're just integrating one of our volume. We get the volume of our cell times the determinant of our lattice constant matrix. So O, in fact, is precisely the same thing it was before. It's the identity times the determinant of our lattice matrix. In fact, you don't even have to change the code on that one. Because your code, if you were smart, or when it comes up, do we have O? Yeah. If you did the code on the Poisson equation, all you do is you take your input vector and you multiply by that scalar. So that's not going to change. So no change there. That was easy. All right, that one's down. L next. You see, it's pretty easy changing basis sets. L. again, that's going to be integral b beta star del squared b alpha d cubed r. Well, we can go through it if you want. It's the same thing we had before, right? You're going to have a minus sign because the del squared pulls out two factors of I. You're going to have g alpha squared. You're going to have then just the overlap between them. So that will give you a delta alpha beta times, again, the volume of the cell, determinant of R. So now L is just same formula, minus determinant of R times, at least on a formal level, diagonal of G0 squared, G1 squared. That's it. It looks the same, but the big difference is we have a different set of G vectors now, right? We've only picked the ones inside the sphere. So we have to modify our code a little bit to make sure we're only dealing with the ones in the sphere. So I'll show you a little Octave and MATLAB code and tricks to make that a little bit easier. The basic idea, and this is kind of a neat function of Octave, is that you can find all of the G vectors from your box that fit inside your sphere very quickly. So again, the idea is I've got this big box, and I just want the ones that are in a certain sphere. And I'd like to make a list of which ones they are, so that I can work with them. And the way in Octave you would do that is you would say, we're going to call the list, say, active. So this will be an array of which G vectors actually live inside the sphere that we're going to use. And the way you do that in Octave is you just say, find. You had a quantity called G2 on your assignment, which was the list of all the G squareds. Find where those are less than G max squared. And that will just find all of them for you. And that will make a list for you. The list will look something like, well, the first one is definitely going to be in there because that's the 0 vector. And then there'll be, I don't know, 2, 3, but maybe it's skip 4, 5, and 6, and then there's 7, and then 9, or whatever. It'll just give you a list of the indices of all of those G vectors. Good. Now, to make our diagonal element here, what we needed was just the values of the G squareds from the active elements. So you can make another thing, call it G2A for the active subset of G2. And there's a very nice notation here, which I think is quite sensible. That's just take your full set of G2s, that's an array, and index it by that active list. And that will just pull out element 1, 2, 3, 7, and 9, and pack them into a nice vector G2A. Simple. And then if you want to write code for, the subroutine then, it's actually going to look very similar to the one you've already written. If you want to have out equals L acting on in, now all you do is you say, well, out equals, well, there's this factor minus determinant of R, your prefactor, times, and I'll just put extra parentheses in here just so you can parse it, the input vector, and it has to be multiplied element by element by the corresponding active G. So you'll just take G2 active, the list of the active Gs, pointwise multiply, which in Octave is a period and then an asterisk. This will pointwise multiply all your elements, apply your normalization, and that's your output. So the only change in that code actually is you are going to replace where it says G2 with G2A. And it will be the same piece of software. Simple. Good. So that's O and L. I. I's going to take a little more thinking. I think we'll leave it there for today. Okay. Good. And next time we'll get the other $250,000. Let's see.